All right. So hello, everybody. Welcome back to the GBO Colloquium series. It's been a little while since we've virtually seen you all, but I really appreciate having you all join us here today. And so to get things started, we have a talk from Grace Chesmore. She's a PhD student at the University of Chicago. She's working with Jeff McMahon, excuse me, sorry, Jeff McMahon's experimental cosmology lab, focusing on characterization and modeling of complex optical systems for millimeter wave experiments. But she is also a part of the Simons Observatory, as well as the Atacama Atacama Cosmology Telescope collaboration. You can tell I haven't had to introduce someone in a while. And is a Department of Energy Student Research Fellow, working at the Fermi National Lab, developing a detector with Dr. Sarah Simon. So, Sarah, when you're ready, if you would please share with us what you're working on.
Okay, hi everyone. I'm really excited to give a talk to fellow astronomers and radio astronomers at that, because usually in Chicago I'm giving talks to I guess different wavelength astronomers. So this is very exciting. So my name is Grace, and I like Jesse said, I work with Simons Observatory and the Atacama Cosmology Telescope, which both are aimed at measuring the cosmic microwave background, which I will go into in a bit. But my role really is to study the optics of these telescopes and try and improve them to the best of our ability. And that includes modeling and measuring these optical systems. And so on the front slide, you see 3 beams. So these are the beams that I will be talking about in the presentation. Really, all I do is just look at beams and try to make them look as nice as possible. And in turn, that gets us a nicer measurement. So let's start by understanding what we're even trying to look at with these telescopes. This is a picture of the history of the universe as we currently understand it. So initially, the universe began with a Big Bang, as I'm sure you've heard of, which for a fraction of a second was followed by this rapid inflation. And then for around 400,000 years, the universe was rapidly expanding and cooling to a point where photons cooled and their energy was a bit lower, to a point where they were able to decouple from baryons. And so this is the moment called cosmic microwave background, where the photons were no longer rapidly scattering off of electrons. They were able to free stream, and all of a sudden the universe became transparent. And so this is when photons broke through and they were able to, we usually call this the moment of last scattering. And this is really what cosmic microwave background experimentalists are trying to measure. We can actually detect this radiation from this early moment in our universe. And you can see here with the rest of, all this other side of the history of the universe, this is all just a bunch of stuff that these photons had to travel through before reaching our telescopes. So not only do you have these photons, not only do you have photons that are possibly teaching you something about the early universe, but they're also having to traverse through all this large scale structure in the late universe. So a lot of different physics that comes out of just this moment of radiation. So what can we learn from the cosmic microwave background, which is just this radiation from the early universe? So like I said, there's a lot of late universe. So galaxy formation, there's dark energy and dark matter, the standard model of particle physics. There's a lot of tweaks coming out of the standard model just from the cosmic microwave background and looking at the conditions of the early universe. And additionally, one thing that I think is interesting is taking a map of the cosmic microwave background and cross-correlating it with additional surveys that maybe are at a different frequency range, like the dark energy survey. You can get a wider spectrum of a map in this to look at this patch of sky in a wider range of wavelengths and learn something more about large scale structure. And that's something that a lot of people I know in my collaboration are working on, is this cross correlation between surveys. And so then early universe stuff, right? Because this is really radiation coming from the early universe. The patterns or the fluctuations in this radiation are completely set by the conditions of our early universe. So this includes if they're primordial gravitational waves. This includes the spectral index of inflation, so just the nature of how our universe is inflating. The relativistic species, so this is called N-effective, but it means how many relativistic species existed in the early universe. The rate of expansion, which is the Hubble constant, which right now there's this big tension between how our universe was expanding in the early universe doesn't exactly match how it's expanding now. And so there's this kind of confusion about this. It's called the Hubble tension, and astronomers are and cosmologists are kind of trying to figure out what's causing this tension. So that's an interesting problem. And then extensions to the way we understand our universe. Like, could there be some early dark energy term that's causing this Hubble tension that existed before the CMB? And just as an example of like why you would want to measure the CMB at such a, like, we already have it measured, right? But like, why would you want to measure it at such a higher signal to noise, is because at small angular scales, so this temperature and polarization that we measure from the CMB, if we measure it well enough, we could rule out an entire class of inflationary models. And that's kind of where cosmology is going. We're trying to constrain our understanding of the early universe to the best of our ability. And there's still so much that's just unanswered or could be constrained better. And that's kind of where it's going. So let's talk about the cosmic microwave background, a little refresher, maybe for people who have heard of it, or an introduction. So the cosmic, if you just look at the cosmic microwave background in the sky, it is incredibly uniform. It's like a perfect black body, but there are these tiny fluctuations. So the temperature of the CMB is around 2.7 Kelvin, plus or minus a microkelvin. But the fluctuations themselves are around 1 part in 10 to the 5. So if you were to look at this temperature, I guess, color scale is 1 part in 10 to the 5. And they can be, the way we understand this is basically to break down the CMB into Fourier space. And what does that really mean? It means we understand them in terms of L values. And L values you can think of as really just like 180 degrees divided by theta, this relationship here. So that's where that Fourier relationship comes from. And so if I look at this over here, this is like if you added up all the different multipoles with, you know, some constant in front of them, this is how we understand what the cosmic microwave background looks like. And again, these tiny fluctuations are completely dictated by the inflation and the conditions in the early universe. So this is how we understand it. We break it down into L values. So large L value is small angular scale, and small L value is large angular scale. So there's that inverse relationship there, just to be clear. Okay, so now how do you measure the CMB? So like we talked about in the last slide, temperature maps of the CMB are deconstructed into L space. So here's a picture from a recent Atacama cosmology telescope paper. And the top line is this temperature power spectrum that we get from the CMB. But there's also some polarization to the photon. The photons are polarized in the CMB. And so that's kind of the next frontier, I guess, in the CMB, in measuring the CMB, is getting our telescopes to be really high signal to noise and being able to pick up these smaller scale, like for example, these are called B mode polarizations, and you can see they're much smaller signal than the temperature power spectrum. And within the B modes, that's where you would start to pick out primordial gravitational waves. So these extensions, these higher physics lessons that we can learn require really well constrained telescopes and really high signal to noise. An Atacama Cosmology telescope is a ground-based telescope in Chile. The reason for that is you want a location that's high and dry. Basically, I mean, I'm sure as many of you know, you want as low atmosphere as possible. So that's why typically the CMB experiments are in Chile or in the South Pole. And also, if anyone has any, I'm like gonna every now and then look at the chat, so, or interrupt me if I'm missing someone having a question. Okay, so what is the status of cosmic microwave background experiments? So I mentioned that you have the Atacama Cosmology Telescope. So the status there is that they've been taking amazing measurements. This little picture down here is just a little preview of the maps that they're taking. And they are soon to release data release 6. I work a little bit on that, so I'm not going to be talking about that today, but I can try and answer any questions you guys might have. The number of detectors in that telescope is around 3,000. The Simons Observatory, which is being deployed right now, this is a picture of some of the hardware that I'll discuss in a little bit. The number of detectors is above 60,000. So we're just ramping up the number of detectors to try and increase mapping speed, increase signal to noise, get those lower signals to the best that we can. And then looking forward, already being planned is what's called CMB S4. The planning is in progress for this. People are starting to develop the technology. The number of detectors is up to 500,000. So this is a telescope that will be kind of a multi-parter. So they're going to have one in the South Pole, they're going to have a couple in Chile, and those are going to kind of like harmoniously work together to get all the angular scales that we need to get this really nice picture of the cosmic microwave background. But okay, all of this, if you have really good detectors and you're getting really high signal to noise, that means that you're also going to be picking up all the systematics that maybe you wouldn't have seen with a low signal to noise detector. So this requires really careful understanding and control of systematic effects, which is kind of where my focus comes in. So I'll be talking mostly today about the Simons Observatory. So let's just get a little bit of an instrument overview. So there are 3 small aperture telescopes. So small aperture means large angular scale, or small L value. And this will measure the largest angular scales visible from Chile. So around 10% sky coverage, about a 0.4 meter aperture. This is a little rendering of them. They're about 1.5 meters tall. And one really important aspect of these that I find interesting is that they are useful for characterizing the atmosphere. Because if you have this large angular scale and you can measure one patch of sky at a time, the atmosphere might change over time, you get a quick picture like that. And that is what we use to characterize our atmosphere, and then use that to subtract it out or correct for the CMB maps down the pipeline. So here's that picture that you saw on the last slide. So this is them starting to be built up in Chile now, very exciting. And we actually have one that we're using for a couple different testing purposes at UChicago. So this is my lab mate Shreya for scale. And this is, we have this big testing structure around it, which I'll explain in a bit, but you can kind of see here it is housed here. And so the detectors, the frequency range that we're planning to look at, we have 3 frequency bands. So low to high frequency, we call them, easy enough. And it spans from 27 to 270 gigahertz. And they are evenly split between the small aperture telescopes. And then we also have what's called the large aperture telescope. So this is the very big, this is a little person for scale. This is 15 meters tall, and this is our large aperture telescope. And so since it's the large aperture telescope, it's going to be measuring the smallest angular scales that we possibly can manage with our detectors. And this will go around for 40% of the sky coverage. And the science goals with this guy, because it's measuring the smallest angular scales that we can, the goal is to do, like point source analysis. So cataloging thousands of galaxy clusters, extragalactic sources. You know, this is what you would use to then cross-correlate with data from other experiments. Also, you know, constraining cosmological parameters, right? Because you're getting out this power spectrum of the CMB, which you then fit to the model of how we think inflation would create these fluctuations. So you get out cosmological parameters. So both early and late universe content is going to be coming from this telescope. And here's a picture of this being made right now. This is the elevation structure. So kind of like underneath the bottom of the telescope. This is what's being made here. And stuff's getting deployed to Chile now as well. So that's exciting. And then inside, I'll open this up in a minute, but inside, this is the big receiver. So this is where we have all of our optics. So this is what's being cooled down to around 100 millikelvin because we have our detectors that are cryogenic. And that's where all of the optics is going. We have the lenses that guide the photons onto our focal plane and then read out. And then that's how we're getting the data out of that one. So the first, I'm kind of, during this talk, I'm going to be discussing a few beam systematics that are tricky to solve and then kind of telling you how we're going to solve them. So this is our first beam systematic, and this is pure mirror panel alignment. So with these big mirrors from big telescopes, it's very difficult to make a big mirror out of one piece of material. So what usually happens is they get made out of these panels. And with the large aperture telescope, we have two mirrors and they are each around 6 meters in diameter. And each mirror is made out of 69 to 77 panels. And then each panel on it, so say this is a panel, has like 5 adjusters where you can adjust how the surface shape is. So in total, if I were to look at total number of adjusters on this full telescope, it's 385 plus 345, so 700 something adjusters in total. That's a lot of adjusters to try and get this perfect surface of your mirrors. And so when we order these mirrors, the specs say that they can achieve a surface error, so a root mean squared of the surface error, less than 10 microns per mirror. But current mirror alignment techniques that are used, like on the Atacama Cosmology telescope, for example, they can only achieve around 25 microns. And I mean, that sounds pretty good. So I should explain why we really care about this. So I wrote a simulation that actually messes up the mirror panels in the large aperture telescope and then measures what a far field beam would look like if you ramp up these surface mirrors, the surface offset or error on these mirrors. And so what you're seeing is this first panel to the left is like perfect mirrors, smooth, you get a nice airy disk, which is exactly what we would expect. And then as I ramped up the surface error to 20, 40, 50 microns, you start to see these like random, and these are just random offsets, you start to see some like bumps and wiggles in the side lobes. Now, if I want to quantify how bad this messes up the beam, what you can do is you can look at the window function or amount of signal that your telescope is getting. So with 0 micron offset, it looks pretty standard telescope of your window function, and this is an L space. And so if I bump it up to 40 microns, what this is telling me is that at 40 microns, I'm going to lose about 11% of the signal from L values about greater than 1,000. And then just like as a sanity check, I compared this to the Roos equation, which a brief overview of the Roos equation, and this is just if you have an antenna that has some surface defects, how does this affect your gain? And so this epsilon value in this equation is the surface defect, the root mean squared of the surface defect on your antenna, your wavelength, your standard gain, and then from that, you find what your new gain would be. And so the dashed lines are from the Roos equation. So we said, okay, this seems to match what would be expected given the very simple Roos equation formula. 11% is pretty bad if you're trying to measure those small polarization signals from the CMB. So this is something we should probably look into. So the solution that I came up with was, or that our team came up with, and then I ended up coding up, was holography and machine learning. So both of those, I will explain how we do that. So the first part of this is just to simulate what the fields would look like at the aperture plane, or basically at the opening of the telescope where light comes in. What would the fields look like there? And so with the simulation, I'm able to simulate the half wavefront error on the primary mirror. So the first mirror that the light hits, then the secondary mirror with panel, these are with adjuster offsets. And then this is combined, because in real life, when you're taking a measurement and you're just if you just want to take a picture of what the electric field looks like at the aperture plane, you can't really distinguish between the half wavefront error on the primary or the secondary. What you're really measuring is the electric field of the combined adjuster offsets. And this shows up actually in the phase of your beam. So phase you can think of as kind of like path length difference. And so if you have these adjuster offsets that are kind of both contributing to this path length difference, you're going to see that in your combined phase. So, okay, this was the first step, was just to make a working simulation of the adjuster offsets in the large aperture telescope and see how that would affect the phase. But then what we can do with this in real life is a method called holography. So this is where I was showing you those weird panel looking things on the last slide. This is the aperture plane. And so the idea is that you can measure this using holography. And the way you would do this is you have a source out, like maybe like a kilometer away or something, just a coherent source at one frequency, and you aim it at the telescope. And this would eventually go into, through the primary and secondary and into the receiver. And you would set up a receiver to be at some nominal focus here. Okay, so these are the measurements that you would actually make when you do holography, is that you get this nice point source. And that would, if you had panel errors, you would see something maybe similar to the 20 or 40 microns, depending on how aligned your mirrors are. So what I did is I actually coded this up. We plan to do this in real life, but I coded this up to be kind of a virtual telescope. So that way that I can fully simulate the holography measurement before we even did it. So that's what this is. This is just a simulation of the whole holography setup. Okay, so because I have a simulation, I can simulate a bunch of these far fields at a bunch of different adjuster offsets that are just randomized. And this will give me an idea of how the beam looks given a certain set of adjuster offsets. So because the half wavefront error of the combined is what we can measure, this is really what we get out of the far field beam. So once we take a measurement of the far field beam, we can get out this half wavefront error combined. And then we said, let's try and use machine learning so that we can just say, okay, we have a ton of these simulated half wavefront errors. Given a ton of these sets of adjuster offsets, train a machine learning model here. And this is just a very simple application of machine learning. This is using an ordinary least squares method. Just wanted to see if it would work. And then we fed in a new holography simulation. And this is what would be taken and will be taken in the field. And then what it spits out is the adjuster offsets. So which yielded out this half wavefront error that it predicts that you would get. Right, okay. So what we found from this is that given a new simulation, the machine learning model is able to fit pretty well to what it thinks the adjuster offsets should be. And the residuals are consistently below 10 microns. So this was great. We figured, okay, we can use this method when we go to the site and do holography. Okay. However, our focal plane is about 2 meters wide. So, you know, things looked really good when I was doing everything that we've talked about so far. I was assuming we were like dead center in the focal plane of the telescope. But as you have detectors that are kind of more on the outside, things start to degrade a little bit with this method, as you can see here. So I wanted to kind of quantify that. So this is this first panel here, or this first row, is looking at the half wavefront error root mean squared, like after doing the fitting and everything, as a function of the focal plane position. And you can see this red dot is where we trained the machine learning model, the position of our receiver with the machine learning. And it really degrades as you get out to wider scale, wider angles, wider radii, from the focal plane. And this is due to the fact that you have a primary and secondary mirror. So like combining these two, combining the secondary and primary half wavefront error probably looks really good to the center. But as you move out, it's almost like having one eye, you don't have depth perception. And so what we figured was if we added one receiver at the top and one at the bottom, this might be a way that we can regain some depth perception and try and get over the degeneracy between the two mirrors. Because that's really what was going on, is there was just a degeneracy. It's hard for the machine learning to figure out which one is causing the adjuster offset in the wavefront. So that worked pretty well to add 2 receivers. But we figured it's still not working out so great at the wide angle. So we added 3 in kind of a equilateral triangle pattern in the focal plane. And we said, okay, this is consistently getting us 4 microns of the half wavefront error root mean squared over all but the edges of the focal plane. So we figured, okay, this is the method that we are going to use when we eventually do this. And we're in preparation for doing this now. So a lot of this was simulation, but I wanted to bring it into reality a little bit and explain how this would be done in real life. So the plan is day 1, take a holography measurement. Okay. Day 2, simulate the training sets with a specific instrumentation setup. So receiver position, source position, frequency of source, anything else and this can all be changed in the code to adjust your simulation. So then you're going to train your machine learning model. And then day 3, you would use the machine learning to get the adjuster offsets. And you go out into the field, you adjust the panels by specific adjuster offsets. And then you would go out on day 4 and repeat the holography measurement to quantify the new surface defects. And the great thing about this method is that, this whole thing, let's be generous and say it takes us a week to do this. This is basically 1 iteration of fitting. And so it's really ideal to have this fit only in 1 iteration. So 1 machine learning time around to get it down to the 5 micron surface root mean squared, as opposed to doing this, adjusting the errors, having to go out a second time, adjusting the errors, because it just takes a lot of time. So this was ideal for us to, as opposed to other methods to try and reduce surface defects in mirrors, this is one where it would really only take 1 iteration to do this. And we have a student at UChicago now who's preparing the hardware to make this happen. And so coming from this, there's open source code. It's called HoloSim-ML. And what it does is it can model the aperture field with adjuster errors on the primary, secondary, and combined using ray tracing. So this is a big ray tracing open source code that I wrote. And it consistently gets the path length, the path length root mean squared is consistently below 10 microns. And beyond this, if you didn't want to do any of the machine learning part of it, there is just the piece to simulate what the far field would look like with adjuster offsets. So you can see on GitHub, it's all public, and it was published in, I believe, 2020 in Applied Optics. And yeah, so that is that. And then, so the next beam systematic that I want to talk about is actually something that was seen in the Atacama Cosmology Telescope. So this is, I'm like not even joking, this is called Little Buddies, mostly because they didn't know what they were. So they just gave them a cute name. So these diffraction spikes that you're seeing here, these kind of like spread out at 90 degrees. These are what are the little buddies. So these are an optical effect that were not really well understood. And when they first saw them, it was like, okay, there's some side lobes, not really sure where they're from. But what they do cause is temperature depolarization leakage in the power spectra of the CMB. So when you're doing your analysis and you're trying to see, okay, what's the temperature power spectrum? What's the polarization power spectrum? What you're actually getting is a little bit of the signal that's crossed between the two. So the solution as a, oh, and I also wanted to share, this is a filter that is used in the Atacama Cosmology Telescope, or the type that is used. And you can see kind of the cross pattern. Like you can see there's like a bigger kind of cross. And then there's also these really small squares. And the purpose is, this is supposed to be kind of a an infrared blocking filter. So to get the cleanest band you can get, they use these filters to kind of clean out frequencies they don't want. But as a unwanted byproduct, when you have a square aperture, in Fourier optics at least, this can create kind of vertical and horizontal diffraction spikes. So one of the thoughts is that this could be a byproduct of having these filters at certain positions in the optics tube, but it's not really clear, you know, it's still not really clear what exactly is causing this, but this is one thought of what could be causing it. So the solution as of right now for this side lobe, for this systematic, is all in the analysis portion, really. So the analysis in the analysis pipeline, you take your CMB map, okay? You look at a few of these Saturn, so maybe you point the telescope at Saturn or another really bright source, and you get an idea of what these like spikes generally look like. And you model them, and you take them out of the rest of your map. So you model them, you get a power spectra of how this is going to affect your CMB map, and then you take it out. All done in the analysis pipeline. So the idea was, what if there was a hardware solution that could maybe mitigate this problem before everything was deployed and everyone was like taking data? So that was kind of the motivation of what we have going on at UChicago. So before we get into that, I have to open up the large aperture telescope a little bit. So this is the same guy that we saw with HoloSim-ML. So this is the receiver. If I zoom in on the receiver, this is the whole thing that is cooled down to, well, the focal plane gets cooled down to 100 millikelvin. And within the receiver, there is location for 13 optics tubes. We're starting with 7. But the optics tubes, again, are like what has all of the optical components to guide the photons onto the detectors. It has absorbing tiles to reduce scattering. It has baffling filters. It has a Leo stop to define the shape of the beam. This is where all the like optics, like nitty gritty stuff is happening. So this is what we want to test. We want to test to make sure the optics tube, oh, and sorry, it also includes the filters, like the ones that have that like square pattern in it. So we wanted to test this, make sure it was all looking good. Okay, so what we did was we took this optics tube and we flipped it vertical, and we actually housed it in that small aperture telescope just for testing purposes. Like we were like, we just need something small to cool it down so we can do all of our tests on it, and then we'll deploy it. So this is actually what we have at University of Chicago. And so the goal of my piece in this project, so there's all these different tests that are going on and integration at Chicago. My role is the optical performance, or the free space optical performance of the tubes. And this is a picture of the optics tube at Chicago. This is all the electronics for my measurements I'll show in a minute. But we have the optics tube housed in this, the small aperture telescope. The focal plane is sitting at the bottom. And this metal structure around it is what we use to mount all of our testing equipment on top of it, and do all the various tests that we set out to do. So this is, if you're to look on the top of this, the tester, this is the hexagonal window. The window has HDPE, high density polyethylene. Basically what you use for a cutting board really is used for our windows. And this is our source that we use for beam mapping. It hangs down from this motorized XY stage that scans above the window, sending a signal into the optics tube. And this is just more like fun pictures of taking the telescope apart in lab, building it back together, keeping everything cold to the best that we can. Yeah, this is us putting the optics tube into we flipped the whole thing upside down, and this is how we kind of hang the optics tube into the tester. And this is just another pretty picture of looking at it from the side. This is the circle here is where the optics tube would go, but it's empty in this picture. Okay, so this is actually performing holography. So this is a really fun experiment that I got to do. So basically what holography is, it's just a fancy way of taking a vector beam map, so measuring the amplitude and phase of the beam at a certain plane in space. And the reason this is so attractive as a measurement is that you can use this beam at one plane in space to understand how the electric fields will propagate at a different location in space. So that's kind of the idea. Now, the way this works, this is a diagram of how the experiment works. You have a source here, this little feed horn that's hovering over, like you saw in the picture below, hovering over the optics tube. And this scans in the XY plane. And then you have the signal that's received at the back of the optics tube being carried out, and a bit of the primary source is also split off and taken to an FPGA. And this cross correlation gives us the amplitude and phase of that point in space where the source is. So you can think of it as kind of mixing a modulated through the optics tube with a non-modulated signal to get something out. And then that's fed to the computer. And then with analysis, we get our beam maps. And so this is a picture, this is the source above the optics tube. And then this is a receiver in our focal plane. These are, this is the usual Simons Observatory waveguides that are used to fed out the signal. But then we adapted them to use this coherent receiver that I use for holography. And so that's what you're seeing here is two receivers that are just different optional spots that we can use to measure at the back of the optics tube. So let's see. Oh, it says video cannot be loaded. That's okay. Let's see. There we go. So the results, we took beam maps of 80 to 170 gigahertz, and we did this in 10 gigahertz increments. And so what you're seeing here on the top is the amplitude, and then the bottom is our wrapped phase measurement. And so what we noticed at the beginning when we did this was there seems to be like some extra power, like, I don't know, like in the outside of the main beam. And we were kind of confused as to what that was. So you can see like the 150 doesn't seem to have too much power outside of the main beam, but maybe 100 gigahertz has a lot. So what I did was I plotted the amount of power outside of the main beam as a function of frequency. And you can see that's the red dot here. And so there's some weird like frequency dependence that we had no idea like what was causing this. And so I plotted all of the filters, all of the reflectivity data that we had of all the filters in the optics tube to see if there was some similar frequency dependence. Maybe a filter was causing this weird reflection, like we just didn't know. And what I found was the 1K, so the 1 Kelvin, the filter that's cooled to 1 Kelvin, low pass edge filter had the most similar frequency dependence of any of the filters in the optics tube. So what we did was we opened up the telescope again, we took out that filter, we closed the telescope back up, and we tried this whole thing again. So these are all the same beam maps you just saw with that filter at the state at the 1K stage. And then this is once we took it out. So I'll go again. You can see the power outside the main beam, and then gone mostly once we remove that filter. So what you're seeing now in the blue line, which is the power outside of the main beam as a function of frequency, we were able to remove that amount of reflected power that was going into the side lobe. So this was great. We said, okay, in total, we've removed the side lobe power by 4%, which was phenomenal for like having your detectors not see stray signal, for example. And then the next thing that you can do, a really convenient relationship with radio holography, is the relationship between near and far field. So the Fourier transform of a near field is the far field and vice versa. And so I basically took advantage of this relationship to Fourier transform the near field measurements that we had gotten into the far field and propagate it. Really, basically, I'm looking at what it'll look like on the secondary illumination. So this secondary mirror here. The red outline is the outline of the secondary mirror. And I did that with all of the beam maps. And so again, this is for all the frequencies. This is where the beam is going to end up on the secondary mirror. And the reason this is important to quantify is because any amount of power that goes outside of this red boundary is like we say it's lost, it's spilled power that's a loss to 300 Kelvin. So I quantified this by integrating the total amount of power inside the red boundary, dividing it by the total amount of power in the map. And what we found was across the mid-frequency mid-frequency measurements, we see around less than 1% spilled power, which for Simons Observatory, our requirement was 2%. Okay, so we were very happy with that also. Our optics, so far, so good. And then lastly, we wanted to propagate fully from the near field measurements through the large aperture telescope and into the far field. And so the way you can think about this is we're basically predicting what a point source would look like from the telescope's point of view only by measuring the near field in lab. And this is a bit trickier because first of all, you have to have the rays bouncing off of the two large aperture telescope mirrors. Then to really build up a simulation of this, you have to simulate the full optics tube that we have that we're really testing with the mirrors and everything. So making sure everything is spaced correctly in your simulation. And so the way we did this was I used the same virtual telescope that I coded up for HoloSim-ML that we've talked about. And so with that, I basically took my near field measurement and I placed it in this virtual telescope in my simulation. And I kept those fields there. Then I had this source that I said was in the far, far field, so like 100 kilometers away from the aperture plane. And I ray traced through the entire large aperture telescope and onto that same plane where my measurement was taken in lab. And then what you do is by multiplying the electric fields and integrating over the area of your aperture, that gives you the amplitude and phase that the telescope sees for that pointing of the telescope. So then, because it's a virtual telescope, we can just rotate in azimuth and elevation and build up our full beam map. And so that's what this picture is here, these panels. So this is our averaged for the F90 band, which means just the lower half of the frequencies that we've taken. This is the propagated measured beam into the far field. And then same thing here, this is our propagated F50, or the top, the higher frequencies that we measured. This is them propagated into the far field as well. And then I was able to simulate the optics tube itself and propagate that. So I had a full simulation of this telescope before even deploying. And comparing the two, we found that the beam sizes were in great agreement to what the telescope was designed to do, which is important. You want to have a nice resolution of your telescope. And then also we found that the side lobes or the amount of power outside of your main beam is around minus 20 dB, which seemed like was sufficient for our purposes as well, for the signal to noise that we're going for. So a couple things came from this. We had open source holography, and this is this is all on GitHub, by the way. So this is a website that explains how to do all the hardware with this. So including the hardware of like the setup, the FPGA that we use, the spec sheets, and then also the software. So tutorials on how to program the FPGA, how to talk to the synthesizers to make the signal, and kind of piecing it all together to make this measurement possible. The second piece that is soon to be published with the paper on these results is modeling the Simons Observatory large aperture telescope optics. And with that, let's see, I don't think the videos are loading today for me, but here we go. But what you can do is you can build the electric fields anywhere in the optics tube. And this is really useful if you're doing these tests in lab because, you know, say I am doing a measurement in lab and I know my source is like 11 centimeters above the window, I can go into my simulation and change that manually and then have a one-to-one comparison of the beam shapes and then what I'm measuring and kind of figure out what's going on. So this was really useful to me when I was kind of debugging the setup and figuring out how big should the beam radius be at this point. You know, am I really in focus by looking at the phase measurement, that kind of thing. But then also with this, there is the information for how to propagate this near field beam into the far field to determine the telescope beam, predict the spill and systematics in the far field and also from near field, and can be, you know, tailored for different radio telescopes as well. So in conclusion, 3 beam systematics that I talked about today. One was the HoloSim-ML with that panel mirror alignment with machine learning. And the outcome from this was that we figured out how to improve the window function of the LAT by reducing antenna defects, which has been and will probably continue to be a problem with these big mirror telescopes. And then there's the large aperture telescope receiver tester near field measurements. And with this, we were able to decrease the side lobe power by 4% and efficiency by 7%, which is great for, you know, getting these higher sensitivity measurements. We also confirmed there were no little buddies, which was exciting. We didn't see that same issue going on. And then propagating it into the far field, we confirmed the resolution and the spill of the full large aperture telescope. And also this is the first time that in-lab characterization of near and far field optics has been performed in the lab prior to deploying. Yes, so thank you to my lab and to that's my advisor, Jeff McMahon, and Katie Harrington, my postdoc, and everyone in lab who helped, my team who does a ton of other measurements that are really cool. Yeah, anyway, thank you. And very excited to hear any questions you guys might have. So.
Okay, and thank you so much, Grace, for that incredible talk. Yeah, so everyone, please give Grace a virtual round of applause. And yeah, I think we can open things up for questions. Right off the bat, looks like Ryan, you have a question? Go ahead.
Yeah, thanks for the nice talk. I had to come in a little bit late because I had another meeting, so I apologize if you already mentioned this, but we use holography here at the GBT to measure our surface errors and then correct for them. We don't employ like a machine learning approach. We just, there are people who know on the call who know more about this than I do, but I think we basically just take the Fourier transform of the holography map and then map back out what the surface deformations are. And on the large scale, we use these Zernike polynomials to basically fit the determine a fit to the large scale surface errors that are mostly due to thermal deformations. So I was just curious if you explored more of like an analytical approach to determining what the kind of like surface errors were, or and if you did, if the machine learning approach has any advantages over that.
You mean like the larger scale, like on the mirror? Is that what you mean? What do you mean by analytical?
Well, so yeah, maybe analytical is not the right word to use, but rather than feed the results of the holography maps here into like a machine learning program that tries to figure out what all of the different surface panel adjustments need to be.
I see what you're saying.
Fit these different higher order, several orders polynomials to it, and from that we get a solution for what the surface deformations are.
Yeah. Okay, so yes, I did try that. So what I was trying to do, maybe not with Zernike polynomials, but with basically fitting it to, like taking a simulation and fitting it to some model that looked like surface deformations and fitting it. And because of the degeneracies, because we have two mirrors, it was so difficult to get out like in one iteration. That's the other thing, is we were trying to get this working in one iteration of fitting, and it was just too slow to get low enough surface corrections with multiple iterations. It like wasn't working. And so machine learning, I think that was kind of our like desperate attempt to get like overcoming these degeneracies really in the half wavefront error in a more efficient way. That was the motivation. So I think that's what you're saying. I did try doing like just straight up feeding in the half wavefront error into a model and fitting that, but it ended up taking like 7 iterations, and the goal was really to get it down like below 3. Does that answer your question?
I think so, yeah. So we also have a secondary mirror here, and I would be, this is getting outside my area of expertise. Maybe this is a conversation people have offline, but I would be curious to hear what the people in Green Bank who are more expert on our holography routines think. I know that speed, it's not super fast in terms of the processing. So maybe we're basically in the same boat, but we just can tolerate that a little bit better. But I also would be curious to hear what other people in Green Bank think about maybe using this machine learning approach and if that could actually speed up our processing. So anyway, I think it's all really fascinating stuff. And like I said, that's probably better for an offline conversation with relevant experts, but all good stuff for everyone to think about.
But yeah, I would definitely love to talk to people at Green Bank about like how they're doing, like the specifics of how their process works. So be cool.
All right, thank you, Ryan. I know we only have a little bit of time left. Let's see if we can get everyone with questions to come through before the hour in case people need to leave. So go ahead, Emily.
Okay, yeah, so mine's pretty similar to Ryan's. Thanks, Grace, for all of this information. So my question was actually about the machine learning process, and it's a piggyback off what Ryan was asking. So what does the machine learning approach add that the analytical did not? It sounds like it just made it faster. And why did it make it faster? Is it just because it can run through so many more, I guess, models that you can't do analytically?
Yeah, it definitely sped it up, I think, because I was able to just feed it 1,000 training sets. And then as soon as you do that, like you have your model and you don't have to do that again. I think that was really nice. Because if you're doing this fitting every time, you have to like kind of go through that a bunch of times. Whereas with this, it's just like one time of training a model and then it's like kind of set. I think that was kind of the really appealing part of this. Yeah.
Okay. Yeah. Really.
But I'm interested in thinking, like hearing what other people think of other ways that could speed this up. I think.
Yeah, I think it could be interesting to explore that here. Andrew's on the call here, who has been doing the holography here, and right now we're doing it through a MATLAB notebook. So I think we'd have to convert that to Python first before we could do the machine learning aspect. But I think it could be interesting to pursue that. But yeah. Okay.
That's
thanks.
Cool. Yeah.
All right, and Ellie, you have your hand up.
Yeah. So I think my questions are in a similar vein as previous two, but so I guess my first question, just kind of from a practical aspect, of us being able to do something like that here, is how many, I guess, holography maps, would you need to feed into that initial machine learning model in order for it to be like enough, to see if we could even have enough telescope time to do that, basically.
Yeah, you would need, I'll go back to like I'll go back to the slide where I have like the focal plane thing. Okay, so you would need 3 focal plane positions, ideally in this like equilateral triangle position, because that's where you're really like covering the widest amount of the focal plane to get the most information into the machine learning model. So that would be needed. I would say one of these scans probably takes a few hours. So it would be maybe a day of if I had to estimate. I don't know. It also depends on how high resolution you would do it, but I think order of magnitude, I think each map takes a couple of hours.
Okay, and then but you said you had like 1,000?
Oh, I see. So no, you're totally fine. So the idea with this is that you simulate the 1,000.
Okay, gotcha.
Then those are your training sets.
Great.
So you use that in the model. Yeah, sorry.
No, that's totally good. Thank you for explaining that.
Oh yeah,
so
no problem.
Last question, part of that question was just like the HoloSim kind of software. Is that like, would that be pretty easily adapted to another telescope system, or?
Yeah, I think so.
Okay.
Yeah, so I think there's a piece of it where you define the surface of the mirrors, and so that would be and it'll take like a bit of finessing, only because the way I did this was our mirrors have like a CSV file with like all these parameters to make the mirror. So just swapping that out for something to define the mirror surfaces would be necessary. And then, but other than that, yeah, I mean, especially if you're having a 2-mirror system already, then I think it could be easily adapted.
Yeah, so I guess right now our current surface performance is 250 microns, but we're limited by the actuators to 50. So the actuators can get as accurate as 50 microns. So
okay.
Yeah, thank you so much. This is
cool.
Fantastic.
Yeah, thank you.
Okay, and I think unless there is one more quick question in the audience, which I do not see, then I think we will wrap things up. So let's give one final virtual applause to Grace Chesmore for joining us today to learn about her work, which we'll be excited to see put to use, the Simons Observatory, once that is fully operational. And to hopefully actually get you to come visit us here.
Yeah, that would be fun.
At Green Bank. So anyway, with that, I want to thank you all for attending, and to remind you that we will have another colloquium talk on June 30th with Green Bank's own Annika Schmideke. So thank you all very much and have a great rest of your day.